Yeah, okay, there we go. We're in.
We're in.
Okay, very
Okay,
good.
but then all you have to do, let's go to full screen. Now you can still, yes, share screen, sure. Now we go, where are your slides? This one?
PowerPoint. Oops, PowerPoint. Yeah, okay.
Should work.
From beginning, right?
Yes.
So where's
You
the
go to slideshow, you go from beginning. Now it works.
okay, amazing. Okay.
It should work. Yeah, microphone is the last thing.
Oh,
No. We should have some microphone somewhere.
In a drawer, yes.
there, it's
This one?
even on. No? Is that?
Yeah.
Push a button.
Push a button.
Oh, yeah.
Yeah.
I have to take out my shirt.
Okay. And this is our special point.
Okay. No, I like classical points.
Yeah, this is what I mean. It's our special point.
Okay. Good.
All right, listen, we already spent some time, so I will spare you a long introduction. Especially since Patrick doesn't need too much introduction in the physics audience. Yeah, so
Okay.
the most important thing to know about Patrick that he won a Larkin Prize.
Okay, very good. Yeah, thank you. So, okay, yeah, so I want to talk to you about quite different topic from yesterday. It's about what happens to strongly driven superconductors. And so there's some history to this. So I want to first introduce you to the topic. Turns out that there has been a number of experiments that have been carried on in the last decade that has gotten a lot of interest. But the interpretation has been, I think, rather unclear. And then I claim that I now understand at least one case, which is a Cuprates, which is an important example. So I will spend most of my time talking about this. Organic is a little bit more. I don't think I'll get to the organics. Okay. So there has been okay. The video is not showing me, but it's okay. People don't need to see. It's online, it's okay? Yeah.
I think when you share the screen, you choose the PowerPoint.
Okay. Is this okay now online?
No, you want the online documents, you can change.
No, somebody has to help me. Somebody needs to help. I guess I'm not seeing.
Yeah, I need to try to redo the share. Share screen. I think this is the correct screen.
Oh, is that right? Okay. So how about this picture? Can I get people?
Do you want
my
to-
camera? No. That's not so important. People don't need to see me.
Let me see.
They can see the slides, okay. Right.
We can see the slides and we can see you projecting the video from your camera.
Okay.
Oh, okay,
that's
very
good.
good. Okay, so if I stand here, you can see me. Yeah, okay, yeah. So the experiments have been mainly conducted in Cavalleri's group in the Max Planck Institute. And so what he does is that he has very powerful laser that he can shine onto objects, and he does pump probe experiments. So he shine a very short pulse, and he measures very short time later. Okay. And so the claim is that when you do this, they claim to see superconducting-like behavior at much higher temperature than the transition temperature. Okay, so these are superconductors. When you do this, you see this by much higher. I mean, factors of 2, factors of 3, factors of 5. Okay, so it's not fluctuation phenomenon. Okay, so I have to explain. So he has done this in three materials, three systems, three groups of material. First is a high temperature cuprates, which I think probably a lot of you know something about. And there are two classes of these, LSCO and YBCO, that are quite different now. The second is the organic superconductors. So I briefly mentioned this class of material yesterday. I talked in terms of spin liquid, but turns out that if you make a variation of this, it becomes a superconductor. It's in fact a very high temperature, 12 degrees, the highest PC that we know. And the third case is a buckyball superconductor, K360. Okay, and these are of course also very interesting material, and the ambient transition temperature is 20 Kelvin. Okay. Now, so what does he actually see? So he popped it far infrared and probed and then you can measure the real imaginary part of the frequency-dependent conductivity, right? And the time scale is like picosecond. No, yeah, picosecond. Is it picosecond? Oh. Hundreds of femtosecond, second, yeah, but sub-picosecond, yeah.
Translate the pump. Like.
Oh, yeah, physics, yeah, I'll get there. But it's typically it's yeah, it varies, but it's I would say it's like maybe 50 millivolts. Yeah.
But can you, one question I always had, can you reinterpret that as optical frequency, because you're measuring out of equilibrium? Is it obvious that it can translate to something that is a frequency dependent optical equilibrium?
Well, it's linear response. So it's whichever linear response.
Okay.
Okay, you can call it whichever you want. It's not equilibrium, but it's a linear response of whichever that object is.
All right.
Okay, so that's fair enough, right? Okay, yeah. Okay, so let me start with this clearest. The data I think is clear. So C60 is your buckyballs, and they form a typically basically crystal fascinating. Now, at low temperature, so what is being measured is the reflectivity, and then signal 1 and signal 2. Okay. So let's focus on signal 1 and signal 2. So with this technique, they actually directly measure signal 1 and signal 2 because they do so-called time domain spectroscopy. So you don't need the chromatography. So this is focus signals. So in normal state, you have the Drude behavior, signal 1. This frequency on the log scale. Okay. You have Drude behavior. So the real part looks like this. And in the superconductor, when you go superconductor, then you have a gap, right? And this is a gap, about 6 millivolts, quite large. Right? So this is what you expect for superconductor. And this is in the low temperature state. Now the imaginary part of signal 1, in normal state, again, is kind of Drude-like. In the superconducting state, it goes like 1 over omega. So that's the important thing. Okay? Because it's a chromatographic, it's a real imaginary part. So this is you can say that this is the important signature of superconductor is that the imaginary part of the conductivity goes as a superfluid density divided by frequency. Okay, so that's we consider a signature of a superconductor. Or if you like, you Fourier transform this, then you get a delta function at the origin. Okay, and yeah. So this is what you see in the superconductor. Now, when he pumps it, when he shine intense pumping and then he measures it with this technique, what he sees is this. Okay, so again, this is beautiful. Now you see a big reduction of the conductivity down here, okay. And the real part goes like this. Imagine part of that. Okay, so it looks like this, looks like this, this looks like.
This is again for the buckyballs.
Yeah, this buckyball. Okay, so that's the claim that this behaving like a superconductor. Okay. Now the superconductor, the organic superconductor is the same way, very similar. Now this pay attention to sigma 1 and sigma 2. Sigma 1, yeah, this is low temperature. You see a gap. Is that right? Yeah. No, sorry. This is already above TC. Yeah. Okay, this is already above TC. You see a reduction, looks like a gap-like feature, and then the gap starts going away. But the important point it emphasizes that the real imaginary part goes over. Okay. In the case of organics, the gap is so small that you cannot see the gap optically at below TC. Okay, so this is the first thing that makes you wonder. This is an enormous gap. This is 100 away from the 200 away from it. It's like 10 millivolts. Okay, the enormous gap. Okay, so that already makes you worry a little bit. Okay, whether this is superconducting behavior. Yeah.
If they ever tried this for YBCO superconductor.
Yeah. I think they've tried many things, and these are the only three
Okay.
materials that they can succeed.
Yeah.
Okay. Even within the buckyball, if you look at cesium dope, so only potassium dope. It's very special.
By succeed, you mean see this signal.
See this behavior. See this, particularly it's one of omega that they like to emphasize. Yeah.
And in other cases, when they didn't succeed, they see normal state behavior.
Yeah, it's just they see heating, which is more typical, right? This is the opposite. Sigma 1. You see more. Sigma 1 goes up. Okay, so sigma 1 going down is success for them.
And what would you expect for charge density wave order?
Hmm?
What would you expect for charge density wave order?
You might see a gap, maybe. Yeah, but this you won't see this. Because to see this, you need a delta function at the origin. See, what is not measured here in sigma 1 is that there's a delta function here. And that delta function is responsible for the 1 omega. I promise chroming. So in the charge density wave, you see this, right? But you won't see it. Okay, so
I would argue that, maybe it's 1 over omega in this particular case, but more broadly, it's not necessarily 1 over omega, quantum frequency.
yeah. So,
At certain.
but I think to be fair, I think it's fair to say that as long as you see this, there has to be a peak in the real particle omega somewhere below that frequency that you see this. Okay, so there has to be a spectral way down here.
But it doesn't have to be at.
It doesn't have to be at 0.
So,
Yeah, but it will be pretty narrow. Okay, right, so that's a challenge. Right, and I think this is the reason why they emphasize the imaginary part, because you cannot see below 4 millivolts, and then, but what they can say is that there has to be a. All right. So that's the experiment. Okay, now why do I do this? Okay, I skipped the Cuprates because I'm going to come back and give you more detail. Turns out that the Cuprate experiment is quite different from this. Okay. What they see is actually quite different. Okay, so just the first question you might ask is that what's so special about these three materials? Okay, what's it turns out that they all near the Mott transition. My favorite topic, as you might. Right. So now for the Cuprates, well known, right? Is you dope a Mott insulator. So this is what we call doping control, right? You start from one insulator and you add carriers, and it becomes a superconductor. The organic is what is called bandwidth control. Right? So you stay at half filling, 1 carrier per unit cell, 1 electron per unit cell, and you tune your bandwidth by pressure or by changing chemistry. Okay, and then you go into you talk about methods. So the organic is again well known as something near as I tried to emphasize. The C60 is not so well known, but it was not appreciated in the beginning, but now it is accepted that the C60 is also very close to the Mott transition. And that is known by either chemical doping or pressure So it turns out you can map a universal volume versus temperature diagram. Okay. And if the volume is large, if you expand the volume, then you have an insulator. Okay. If the volume shrink by pressure or by chemistry, then the insulator disappears and the superconductor arrives. And TC is highest nearly this boundary. It goes up to 30 Kelvin. And I think cesium, yeah. So cesium is special because cesium is so big, right? So cesium C60 starts out as an insulator, but if you apply pressure, it becomes a superconductor. So that's a classic experiment. So that's I think what's going to be. But you can make a kind of reversal diagram and KC60 lives here. Okay. So there's a kind of a easy goal. So it's by itself is a fascinating system. Okay, narrow band, probably electron phonon coupling. Yeah, so a little bit more technical, there's 3 electron and 3 degenerate orbitals, so not quite the same simple Mott picture, but the orbital physics. Okay. Yeah, so today I'm not gonna touch this because this thing is really strange. Turns out that for C60, it lives when you do this. This funny state lives for a long time, nanoseconds. In all the other cases, this behavior disappears in a picosecond. Okay, nanosecond for electronics is infinity, right? Even phonons don't live for nano at high temperature lives is a picosecond scale. Okay, so I think that some structural change has been induced here. Whether that new structure is superconducting or not, is a separate question. But I think there's something going on that we need to know a lot more. And I think if you could do structural measurement as a function of this blasting would be very helpful. X-ray or resonant X-ray or whatever. That what can live for nanoseconds, right? So maybe the potassium move or rearrange, who knows? It's driving this thing very hard. By the way, these experiments has not been reproduced by anybody else, not because he's maybe wrong, but because it is very difficult. And nobody else has this kind of resource that they have. That's trying to have the power to this high power research and the time and delay. Other people have tried, but they have less power and they mostly see heating. Okay, but nobody else can get to the regime that overlap with these. Okay, so even though it's not reproduced, I think people tend to believe the data. Okay. Right. Of course, it would be very good if someone else can repeat it, but I believe the data. I mean, I think these guys are responsible people. Okay. Right. So today I'm going to discuss mainly Cuprates. I just mentioned my take on the organics. I don't think I have time to get to that. Yes. Okay. Now the Cuprates again belong to 2 classes. There is the LSCO and then there's the YBCO. So they look at both classes of material. And the experiment is different. Now, the LSCO, the physics is different. The LSCO is known to have a charged ordering, a so-called stripe ordering, and the transition temperature is enormously low at 1/8, so-called 1/8 Kelvin. Okay. TC is typically 10 degrees, for LSCO at 1/8. So they took this enormously low temperature and blasted, and they got 40 degrees superconductor. Okay, but that's not so amazing. So the interpretation which they gave, which I think is reasonable, is that by blasting it, they destroy the stripe order and then restore what it should be. Okay, so for me that's fine. Okay, I'm not worried about it. Okay, now YBCO, as I tell you, is different. So they claim to see this phenomenon up to 400 Kelvin, and I'll show you the data, what I mean. Okay, now 400 Kelvin is no joke, right? So, yeah. Okay. So if you can really induce superconductivity at 400 Kelvin, then even the guy who wrote this there is not. Who cares about it, right? Yeah. But so that's the question. Yeah. So what does it really tell us? That's my goal. Right? Is there another way? First of all, can you explain the data without being too crazy? Right. So I'm looking for a minimum set of assumptions that can explain the data. Right. And then if I do that, then I want to know what does it actually tell us. Okay. I don't want to be completely negative. But so to jump ahead, I think the experiment actually is telling us something very important about Cooper physics, but it is not making high temperature superconductor. Yeah. Okay, so this is what I've been talking to Demler, former student Mario's Michael for several years. And so I think we're finally ready to write something up. So, because they have been working on this for several years with it, and they work closely with Cavalleri. Yeah. Yeah.
Maybe anticipating what you will be talking about. Suppose that there are phase relation existing after 400.
Yeah.
What is the mechanism why pump probe you actually make superconducting transition?
Yeah, that's the whole story. Yeah. Okay. So yeah. So again, to jump ahead, I would argue that the data actually tells you that there's local pair correlation. There's short range order up to 400 Kelvin, but very, very short. It can be 3 nanometers, right? Very, very short, but it has to be there. So you have to have some local superconductivity.
It cannot be charge density reported because charge density reported by YBCO at temperature highest 200.
Yeah, but
yeah, same order.
Yeah, I don't think so. But first, I have to show you the data first. I didn't show you the data. The data is very different from what I showed you before. That's the other point. Yeah. Okay. And because I'm not going to get there, let me just say what I on the organics. I've written a paper with Zhehao Dai, who's my former student. And to make a long story short, our story is that the gap they see is not a superconducting gap, but a Mott gap. So our story is that by driving it, you actually create a Mott insulator that somehow has a very narrow conductance peak at low frequency. That's the anomalous thing, right? But we have a story that allows you to do that. Okay. And the hint for why this is the enormous gap. The gap is 100 millivolt, 100 Kelvin something. It's much bigger. 10 millivolts, yeah. The coherence temperature of organics is 50 Kelvin. The band does not get coherent above 50 Kelvin. So how can you have a superconducting gap that is bigger than the coherence scale, right? So that cannot be a superconducting gap. So we claim that it's a Mott gap, but it has a funny situation where, again, thanks to Yofei Larkin, you can produce something like that. But that's a somewhat, I would say, somewhat speculative story, but
this works regardless of whether the transition is first or second order.
Probably, yeah, because in this case, you're driving it so hard, you just push it over. So the idea is that your thumb would just consume the time, but by driving it, somehow you push it over to the insulator.
But the existence of a delta function in Sigma 1 suggests that it would.
But it's not a delta function. It's not true delta function. Just very narrow. Just very narrow.
You just account for the spectral wave.
Yeah, just very narrow. Yeah, and it's a finite width. But it is a unusual situation. Okay, so for the YBCO storage, I'm going to tell you about, it's more normal and I would say less speculative. I'm fairly confident that we understand it now, even though it's not so easy. Okay, so now I have to explain to you what they actually see. Okay, so the experiment is, I would say, quite different from what's done before. So to understand that, let me first introduce you to the structure of YBCO. So the YBCO is you have a square lattice, and the action is living on the square lattice of the copper. I think the copper, I think the copper is right here. Right. And yeah, the important thing is that you have bilayers of copper oxide. Okay, unlike the LSCO. So the basic structure is that you have two layers of the copper oxygen plane. They're quite close to each other, they're quite strongly coupled. And then they're separated to the next one. Yeah, so this is very better picture. Yeah, you have a bilayer, this is a copper, right? And you go quite far into another bilayer. Right? So the unit cell is this. So each unit cell has one bilayer which is separated to the other bilayer. Okay. Right, so that's very important as a structure. Okay. So each of them would be a Mott insulator. Okay. Yeah. So what did they actually see? Yeah. So what they do is that they pump by using very intense light. This is to resonantly excite these phonons at 16 and 19 terahertz. Okay, 1 terahertz is about 5 millivolts, right? Or 4.5 or 4 millivolts. So this is like it's like 80 millivolts, right? That was the answer to the question. This is this unit. It's very annoying to read this picture. In the same paper, they use inverse wave number. They use.
Careful, we have spectroscopy.
Yeah, but at least they don't use wavelength. That is the most annoying thing. You know, they put lambda and everything is backwards, and I cannot never figure out. But the same paper, in the same paper, they use different. It's very much.
That's why it's only good.
But it's very common in this, because they assume that everybody can convert and they have it.
I think they don't work.
Yeah, okay, anyway. Okay, so they shine this light. And so what is being done is, I think, understood, because there's a resonant mode, there's a resonant phonon that involves moving up and down these so-called apical oxygen, which sits on top of this. So what they're doing is they're shaking this guy up and down. Yeah.
But is this an infrared mode?
It's exactly at this frequency. So this will be 5 infrared, 16 terahertz.
But it's infrared active, but
It is infrared. It is.
oh,
Yeah. This mode. Yeah. Let me just take it up and down. Okay. Right. And there are two of them because there are chains. And then if you happen to shake this one, it's different from shaking the next row. But they are very, very related, that's not true. But having two of them turns out to be important for my story. But these are resonant modes both studied at 16 and a half and 19 and a half. Okay. Right. And so they actually did 2 experiments. The original experiments was again this pump probe directly measuring sigma 1 and sigma 2. But very importantly, now they're measuring the sigma 1 and sigma 2 in the z-axis, perpendicular to the plane. Okay. If they measure it along the plane, nothing. I actually am not sure about that, but I think if they saw something, they would have told us, right? Yeah. So they don't see anything, right? So it's very different from the organic. The organic is in plane conductivity. Okay. So now they're moving charge between planes. Okay, so they're not probing what's happening in the plane, which is what you usually think is similar thing is in the plane, right? Okay, so that's very important to keep in mind. Okay, but the phenomenology is somewhat similar. Yeah. So again, let's look at sigma 2. Yeah, sigma 1. Oh, yeah, this is also very interesting. Sigma 1 is not doing much. This 100. Yeah, this is with pumping, right? Sigma 1 is not doing much. Okay. Sigma 2. Yeah. So this is the normal state. This is without pump. With pumping, you do enhance the sigma 2. And they claim that this is like one of omega. Okay, but for me, this is enough to say that there's some enhancement. Okay? So enhancement tells me that there's some additional weight or something. Something is happening. Okay. Yeah.
One of our function stuff is zero at that.
Yeah, sigma 2. Yeah, why did it start at 0? They must have done some subtraction. Yeah, but yeah, this must be some subtraction. I don't forgot. Yeah, they must have done subtraction. Yeah, so this should be called delta sigma 2. Yeah, I think that this is a better plot for delta. Yeah, so delta sigma 2 is just different. Yeah, it's even different. But the more telltale sign for me is the so-called 1 over epsilon is what is this called as a name? Loss function. Yeah, there's a peak around 30 wave numbers. Okay. Right. So that's your first data. Okay. Right. Okay. And yeah, so to explain this or to get a picture, I have to lead you through something called the Josephson plasma, because I think it's very natural to relate what you see to what is called Josephson plasma, because that's if you're driving things from nuclear plane, you're invoking the Josephson plasma. So what is Josephson plasma? Josephson plasma is just the Josephson frequency, but if there's a capacitance, then when you drive current through it, then you charge up the capacitor, then you're basically an LC circuit, right? You know that the Josephson is like an L. So the LC circuit gives you a finite frequency oscillation. So this is something where if you have a single capacitor and a Josephson junction, this is something that will oscillate as a Josephson plasma frequency, which is given by the frequency square is proportional to the Josephson energy divided by the capacitance. Right. Now, this is for one layer, this is for understood. Now we have a bilayer structure, so things get a little bit more complicated, right? So the structure again is we have this bilayer, and then we have okay. So then you can imagine that there's actually two Josephson plasma frequencies, right? There's certainly is one associated with this closely spaced bilayer, where the charge is mainly oscillating here, right? And this will be at a quite high frequency. And you can imagine that there may be a Josephson frequency associated with this bilayer, right? Now, if you put them together, they're coupled. And furthermore, they couple to light. So this coupled system should better be called Josephson plasma polariton. Okay, and the dispersion is like this. Right, so there's a low frequency mode. Now there's a high frequency mode, which is like this. Okay, where the electric field is mostly between the bilayer, and this is that. Turns out to be about 13 terahertz. Yeah, and there's a low frequency mode where the electric field is mostly down here, and it's about 1 terahertz. Okay, and so naively you would have two things, right? But now you have a polariton, right? You couple to the radiation mode. This slope would be light, velocity of light, very, very steep. Okay, and then just like the optical plasma, then you have this so-called transverse plasma. So this is by analogy to optical phonography polariton stuff. Okay, but you can think of it as just hybridization of the two modes with light. Right. So the mathematics done here, basically the dielectric function has poles, has zeros at these longitudinal frequency, and has a pole at the transverse. Yeah.
So just to clarify, so this calculation is being done, assuming that the layers are superconductor.
Yeah, this is for
So
superconductor.
like kind of
Yeah, yeah, this is a superconductor. Okay, right. Okay. Now, what is known before? Well, there's a long history of people suspecting that there's simultaneous fluctuation much above TC, particularly in the so-called undertook part of the phase diagram. Maybe I go back one. Yeah, so I should say that, yeah, I didn't say. So they did this measurement, okay, and they look for the weight of this 1 over omega, and they can plot it as a function of temperature. And for this doping, this signal persists up to 300 Kelvin. Okay. Right. Now, if they, so this is this data. Standard doping versus temperature. The TC is down here. Right. Okay. And so they have a point here, right? So they start with a 40 degrees TC, and they see this phenomenon up to 300 Kelvin. If they take an even lower doping, 6.45, right? The signal goes up to 400 Kelvin. Very simple. Okay. And if they go further over here, then the signal starts going down. Okay, so this whole thing is a story about pseudogap behavior in the cuprate. And the claim is that this falls under the pseudogap line. Okay, so this must have something to do with pseudogap physics. All right. Yeah. Okay, so I'm going to focus mainly on these. Okay, so I explained that. Right. Okay, so again, oh yeah, what I should have said is that this pseudogap phase is a lot of discussion about what is fluctuation persisting, and there has been some old data from 2011, just optical conductivity data that claim to measure the transverse mode, because you can measure that by optics. So in fact, here, yeah, low temperature, there's a peak here that you associate with, which is 10 Kelvin. Right. So this is the transverse. This is the longitudinal mode. Yeah. So this is again data, right? At low temperature, right? So you get this peak here, which is the low temperature plasma, and I think there's the high temperature plasma is obscure. It's something more. It's this thing here. Okay. And the transverse one is this. Now they show only data at 10 and 200 Kelvin. Back there, Christian Bernhard saw that they can see this up to 180 Kelvin. Okay. That's already very remarkable. Okay. So again, this requires some coherent Josephson response between the bilayer, right? So this is an indication that there's enough simulativity that there's some kind of coherent oscillation between the bilayer. Okay. And that went up to 150 Kelvin, 180 Kelvin. Something like that. Okay. And as far as I know, that's the highest temperature where people can claim to see superconducting-like effects at equilibrium. Okay. So somehow by driving it, they can push it up to 400 Kelvin. Okay. Right. Yeah. Okay. Right. So I think that's I've covered that. Yeah. So that's the previous slide was below TC, and this is what is shown above TC. Okay. Now there's a second experiment which I think is more definitive because it's more direct, and it's a beautiful experiment. So let me spend a little time explaining it to you. Right. So this is the sort of second harmonic generation experiment. Okay, so what is the experiment? You pump at 20 terahertz, right? And you probe, you shine in a probe at much higher frequency. This is the infrared. Okay, it's still infrared, but okay. And you look for second harmonic generation of the pump at double, as twice the frequency. That's why it's called second harmonic. Okay. Right. So again, you blast it with a very narrow pulse. You wait for less than a picosecond, you send in your probe is also a very short pulse, and you look for frequency coming out at double frequency, right? And what they see is a signal is like this. You see ringing. So this is again time domain spectroscopy. You see that the harmonic signal you see is ringing. You do a Fourier transform, you peak. Okay, so that means that there's something ringing, but at these very low frequencies, which is like a 1 terahertz or 2 or 3 terahertz. There's ringing in the sample. Okay. Now, what's the origin of this? It's a very nice picture you have. You see, for second harmonic generation, you have to break inversion symmetry. Okay. Now, the pristine material has inversion symmetry, right? So then you see nothing, right? You don't see any second harmonic signal coming out. You don't pump it. Now, when you pump it, if you're making this charge, if you take a snapshot, you would break the inversion because I have charge up here, right? If you take a snapshot, I'll break inversion symmetry. So if I probe it on this time scale that is faster than this charge oscillation, it would look like it broke inversion symmetry, and I would get a signal. Okay, and then when this slow charge oscillates, then my signal would also oscillate. Okay, so they're living off the fact that you're probing at 10 times the frequency of the pump, but even more so, the signal you look for is at few terahertz. So you're looking for a signal that is 100 times slower. Okay, and this is why you can do this. Okay, so this is the secret of time domain spectroscopy. Okay. Yeah.
The phonon itself breaks inversion symmetry.
Yeah, they see phonon. Yeah,
They see the phonon.
Yeah, so this is the data, right? 5K, you see the phonon. They can fit and identify what phonon. Okay, or the infrared like the phonon. Okay. So what's the tip? But so what happens is that when they pump, then this guy suddenly shoots up. Right? If they don't pump, they have a very, very signal at this low frequency. This is already multiplied by a factor of 20. They see a very small thing. This guy, thinks of it as like a salt up. Now, what is this frequency? It's 10 millivolt. This 10 millivolt is very close to the lower plasma frequency. 1 terahertz of 3 terahertz signal, right? Is very close to the lower plasma. So so this obvious interpretation is that what you're seeing has to do with the lower plasma being excited. But now, when I saw this gave me a great problem, great difficulty, because the lower plasma is the coherence between not the bilayer itself, but between the bilayer. Right? Now, to establish coherence between the bilayers requires much more coherence because they're very far apart. They're very weakly coupled. Okay, so that was a challenge, right? If they saw this at 10 terahertz, the upper plasma, then okay, you can live with that. Okay, right. So this is very hard to live with. Okay, so I was very bothered by this, and then I started looking into it. Okay. All right. So is that clear? The experiment is clear. Yeah. Okay. So my strategy is to run out of time before I can get to the explanation.
Is again found.
Yeah. So that's that. Yeah. I didn't. Yeah, there it is. So there are only two samples. But the signal, you see, that's the signal. Right? It's very beautiful. Yeah. So I think this is actually much more direct because you're seeing something coming out at this frequency. There's no crumbs, there's no signal 1, signal 2, right? Something is ringing at this frequency when you drive it. Okay. Yeah, so that's just very hard to, relatively hard. So there was a paper. Yeah, so this story of this plasma polarization was discussed in the paper by Michael et al. And then they was on this second harmonic generation experiment with Willow theory. But to make a long story short, because I don't think they believe this anymore, and there's problems with it. Their story was that you're pumping at 15 terahertz, right? You're driving this phone now, and you have an upper and lower transport. They say that what you're doing is that you are amplifying these two. By pumping, you're parametrically amplifying these two transport, and then somehow you're seeing this one, right? Okay, so that was their story. And turns out that you have to make it quite, yeah. So in order to make this work, they have to make a rather elaborate story. One thing they have to assume is that the in-plane conductivity is dominated by superfluid component. Right. So that is a problem for me because we know that the in-plane is a metal, right? But in the model, they assume that it's a superconductor. Okay. The second thing that's wrong with it is that, okay, generally speaking, the inter-bilayer Gilson's coupling is very weak, right? So does this mode really survive, right? And the third problem is that you would expect that the upper plasmon would soften as you raise the temperature, right? Because the stiffness and the butter would go away. So if it's softened, then the upper one has to go up because you have to conserve energy. But in the experiment, this thing doesn't change. It's with temperature. It's always at the same frequency. Okay. So I think this theory doesn't work. Okay. It turns out that a much simpler theory works. So my starting point is that what is the minimum assumption that we can make to explain all this data, right? And what it tells us about it. So the new story, this is also with input from the experimentalists because they keep working at it and doing experiments, and they came to realize that the driving mechanism is different. Yeah. So the basic assumption that we make now is that the conductivity is metallic, it's dissipative in the layer. So I don't need any superconductor, even after you pump. But I need to be able to define local phase, state of space and time. So at a given time, I have to be able to see a superconducting phase. Now this phase can be fluctuating with time and can be very short range in space. Okay, but I need to have something there. So that means that I need to have local pairing up to 400 Kelvin. Now that in itself is a very provocative statement. Okay, there's some energy, there's some pairing there, but somehow, they did not manage to get long range coherence. Okay, and I think that's all we need. Oh, the third thing we need is that there is relatively good coherence between the plane, right? So that the phase is locked between the plane, between the bilayer, but they're totally uncorrelated between the bilayer. Within the bilayer, the phase is locked. Okay, so as you know, we understand, these things are Costas-Staulis type picture. The melting is by vortices. So this can happen. Usually, you think about pancake vortices. You have a single layer, right? And the vortices, if you proliferate the vortices, then you get a disordered phase. So here, what I want to say is that the vortices are locked between the bilayer. So these pancake vortices are double vortices. So this can be out. Okay. If they're phase locked and if they run around, if I proliferate these guys, then I destroy the pairing, but I do not destroy the relative phase. Right? The relative phase can still have Gaussian fluctuation, but would not have huge fluctuation that you need. So I think my story can be summarized by this picture, which I. So the idea is that before drive, this is a plot of the phase, the local phase of the pairing phase that I needed. There's a bunch of space. So I take a snapshot. This phase is going to meander by many 2 pi. So 2 pi is here, right? Because there are vortices everywhere. Okay, so the phase is going, and you have a coherence length, which is set by this vortex separation. It may be 2 nanometers, very short, can be very short. Okay. Right, and between layers, they're completely uncorrelated, so the next layer would be spaced with one and they're completely independent, right? Okay. And in fact, yeah, in our story, you can just set the interlayer Josephson coupling to 0. I would just say that they're not coupled at all. There's no charge flow. It still works. Okay. Right, so you have this guy. So the story is that with driving, what you do is that you make this intra-layer phase now coherent. Okay. When I drive, and in fact, they're oscillating coherently, and they're coherent even between layers because I'm driving everything coherently. Okay, so I have this picture, but the overall phase is still meandering randomly, and there's still no correlation between layers. Okay. So the drive in this picture does not enhance any in-plane coherence, does not enhance any inter-bilayer coherence. All it does is to enhance the intra-bilayer.
It almost looks like you've got like anti-correlation between adjacent layers, but is that just?
This is this mic.
Okay, okay, so that's not.
It's supposed to be random,
Okay.
but you know, it's harder to make a random function. Right, yeah. Okay. All right, so that's the message. Now, the details is the following. So we have to modify the parametric amplification process. Remember what they said is that they drive here and then here. It turns out that you have another process which you can abuse it. When you're driving two phonons, you're also exciting the difference frequency. Right, so I'm using you can call it four-way mixing. Right, the difference frequency is at 2.5, 2.8 So now I think I'm driving it at actually 3 terahertz. So I'm going to drive it at 2 Q. And that drive now can decay into two branches. And then I can parametrically amplify this. Right. So now the parametric amplification happens at half the frequency of the drive. I'll explain that. Right. So that predicts that this second harmonic generation DC should be coming from oscillation at 1.4 terahertz. But they saw something at 3 terahertz. Okay. The reason is that they're measuring the amplitude only. Right. So because they see only the output, then they see so the prediction is that the peak of the second harmonic generation. Yeah. Right. And this is given by the drive frequency, the difference of the drive frequency. It works pretty well. And it's temperature independent. It doesn't do much temperature. And it's sample dependent. Between the two samples is always at the same point. So it tells you that there's something intrinsic. Right. So I think that's pretty good support for this. Okay. Now, how does this work? Yeah. So let's consider a single bilayer first, right? So there's the two phases, phi 1 and phi 2. Right? Then the phase difference is a phi delta phi. Then this is your Josephson class 1 equation. This is oscillating at the class frequency. Right? So this is your standard harmonic oscillator drive. Now, if you modulate your oscillator frequency with a frequency omega, right? Then the parametric amplification tells you that if omega equals twice the resonant intrinsic frequency, then you can resonantly enhance, right? Your signal will grow exponentially, right? If you don't believe that, just go back to your childhood, right? Right. This is how a swing works, right? You're pumping, you're driving. When this kid moves up and down his center of gravity, he's modulating the frequency of the oscillator, right? And he has to do it at twice the frequency, right? Because he has one period for him is half the period that you swing. Okay. And this explains why I was never able to get a swing to work because I didn't know this theory. And I always try to move at the period, and I was never able to do it. So now it's too old to experiment. But I don't know, some of you may know this intrinsically, intuitively, you know how to do this. Yeah. But it has to be taught. I mean, I don't think it's very unnatural, right? Somebody has to teach you, but nobody taught me.
But this is a chapter in the first volume of Landau.
Is that right? So by the time you get to the Landau Institute, you know how to get on the show.
How to do this?
Okay.
Can you relax what the capit spam?
Oh, no. This is just harmonic. Yeah. I think that's a different story. Yeah, you stabilize the inverted pendulum. That's a different story. But for us, it's all deep. Okay. All right. Yeah, so that's the story, basically. Let me see. Yeah, so what are the implications? Okay. So again, just to summarize, the drive does not enhance in-plane or inter-layer coherence, but there must be there could be some short-range order overall, but in plane between the bilayer, which are very close together, that's quite strongly coupled, there has to be very good coherence. Okay. And so now, the simple theory, because I'm expanding around zero, the phase zero, requires that there are no vortices, but we think that it's possible that this theory will still work if there is some finite density of vortices, and then we have to figure it out. But that's actually an interesting problem by itself, the problem of parametric amplification in the presence of randomness. Yeah, so we're pursuing that separately. So now with this picture, so this is saying that superconducting pairing locally persists up to here, right? So this convinced me that the pseudogap has to do with pairing gap, is a pairing gap. Now, that is a very bold statement because a lot of people believe it has to do with spin fluctuations and strong correlation and whatnot. But I think this is very rare that this is a pairing gap. Yeah.
This is a story about C-axis.
Yeah.
In the plane, you have disordered state.
Right.
What about artist experiments that claim that they see through the gap by doing measurement of the supposed gap?
No, the gap is in the plane. Yeah, I need that to get local phase. Yeah. Yeah, I need to have some amplitude locally. So the opposite, the pseudogap they see does not require any long range coherence. Right? You just need some short range coherence on the scale of the coherence length, which is maybe 10 micron, 1 or 2 nanometers. Right? Yeah.
But their claim is about this supposedly surviving quasi-particle peak at energy data that you expect.
No, that doesn't survive up to 400 Kelvin, as you know, right?
Yeah, sure.
Yeah. So I'm talking about 400 Kelvin. Right. Yeah, at low temperature, of course, you have coherence peak, and maybe even up to 100 Kelvin, you see coherence peak. But I don't care about that. I worry about 400 Kelvin. Right. Okay. Now, so we thought that we are home free. This is very good. But at the APS meeting, Cavalleri group have some new data, and they claim to see what they call Meissner-like effect. Okay. Now that creates a problem, right? Right? Because I'm saying, how can you have Meissner effect? Well, what is being then you go and figure out actually what did they actually measure, right? So let me tell you what they measured. So the job ahead is to say we actually have a story. We can explain this. So we still survive. Yeah. So the experiment is the following: you have a piece of YBCO, looking from the top. The layers are stacked like this. So the z-axis is in this direction. So the layers are perpendicular to the sample. That's the geometry that they work with. Okay. And they put a piece of zinc telluride here on top. And what they're able to do is, see, this allows them to measure the local magnetic field. So what they do is that they shine another light. The probe is a very narrow focused light beam, and they measure the rotation of the polarization axis. So there's a Faraday effect. So this way they can measure the local magnetic field. Yeah, very clever. And so they claim that they can, if they pump, then they see an enhancement of the local magnetic field. And the picture they draw is that if you have a Miser effect, if you have a Miser effect, right, then you have your flux exclusion, right? That means that the magnetic field here is enhanced just outside the sample, right? So when they say Miser effect, what they mean is that they see a small enhancement of the magnetic field outside. The magnetic field they see is very, very small. It's really Tesla. Okay. Right. But that itself is not easy to explain. Well, it turns out that in our picture, of course, we don't have any kind of current in plane, because I say the current in plane, nothing is affected in plane. But we have some current out of that, right? But in our drive, we are creating current this way. So counterintuitively, we could have a Miser-like effect along this boundary, because I have a current running this way. Then they will create a magnetic field going the other way. Okay. But if I measure in this direction, then I can see nothing. So we actually have a falsifiable prediction that if you do the same experiment here, they see nothing. Okay. So we are going to measure this up before it's falsified. But it gives me some hope, because they only show the data at this corner. And you ask yourself, why did they put in this corner? Not here.
But your argument requires a net current, like a quasi-DC current.
Yes,
Quasi-DC magnetic field.
that's right. Yeah, that's very, very, very good. So there are two things I can say. Yeah, so I don't need because it's transient. This I don't actually need a loop current. Right, and in fact, in this geometry, the current is mainly a displacement current. The physical current is only within the bilayer. But this gives me a displacement current. And in this geometry, the displacement current is the same as the inter-current. I guess it's freshman ENM. So this thing actually has a way of giving me magnetic field as if there's a continuum. But actually, this now goes to the next part that actually that's striking for a long time. The question is what sets the direction of this current? As you know from the swing, when you parametrically amplify, there are two solutions. The kid can go this way or he can go that way. You know, the pump is the same, but he can swing this way. He can start to swing this way or he can start to swing that way. Both will be amplified. So it depends on this initial condition, where it hits to be, where it happens at start. Okay. So if I have nothing else, the pump will give me random current. Okay. For Harmonic generation, it doesn't matter because I'm measuring the amplitude, the square. So that's fine. But for this, it matters because then they will cancel. So I need to set the direction of this pump. And that remains by some sort of so magnetic field. It turns out that now if you look this way, if I have a magnetic field, and now I do generate a circulating current because I have phase coherence within the plane, between the bodies. So I do have this screening current, and on the edge I would have. Now this direction is fixed because the screening current always wants to oppose the magnetic field. So there's an intrinsic current that is running this way, even before the drive, but in the presence of magnetic field. So this is a diamagnetic current. Right. And now if we drive, then just from nonlinearity of the Josephson equation, if I expand it to cubic order, I have a pi squared times its DC term. So then I actually do get a DC that is being enhanced by the end. So at least we can make a story. Okay. Yeah. Okay, so I think that should be the end of my story. The conclusion is that, yeah, I've said it many times before, but I think actually we do learn something very important if we're right about this interpretation about the YBCO, and that there is a up to 400 Kelvin of the pseudogap scale. There's local pairing, and therefore the gap very likely is from superconductivity and not from the.
Kind of one most present question. No. Yeah, Andrei.
When you showed the points in group experiment, you compared with conventional codes to see the gap which come from other experiments. So which experiments you cite as evidence in non-pump probe measurements of pseudogap at 400 Kelvin?
Oh, you mean where this background curve comes from?
No, yeah, go back. Yeah, this one, this picture.
This one?
No, the one that showed phase diagram.
Yeah.
This one is the quarter is fine.
Yeah, this one. Yeah.
And the here.
Yeah.
And the lines are coming out. from
Right,
other-
yeah.
So which experiment you would cite as evidence for pseudogap at 400?
Oh, this line.
Yeah.
Yeah, I don't know. This is from the experimental paper, so I don't know how they draw this line. But there's a standard line you read in the literature, but it kind of looks like this.
Right,
Yeah.
I'm just wondering that you have a special scenario when essentially coherence is along Z direction and the rest is just superconducting station, but with very small
Right.
coherence line.
Yeah.
And I'm wondering, other experiments that supposedly probe in plane,
Yeah. You mean pairing? No, there's no other indication.
this what I'm asking, what does this line come?
No, this line comes from, the standard pseudogap, from ARPAs, from tunneling, from whichever. Yeah.
But in ours, we really probe quasi-particle
Yeah.
in plane.
Yeah. No, that's fine, right? Because
It's another little 100 Kelvin story.
yeah, but in ARPAs, at 400 Kelvin or just below, you may see something like this, right? You see a little dip. That's what they call pseudogap.
Okay, so.
Right?
This is.
Yeah, you see a little dip.
Very extensive. for-
Yeah. You see a little dip, and then I don't know what is other data that supports this 400 Kelvin. Maybe there could be some. But you probably know better than me.
No, I'm just
yeah.
asking that at one point you said RPS is up to 100 Kelvin, and I think this time is up to 400.
Yeah. So 200 is like this,
Yeah, right.
right? But 400 is like this. Yeah. So you still need something, right? Yeah. So it could be a very short range local fluctuation. So I think it's consistent.
All right, then let's thank Patrick. All right, here we go. I have exactly the same picture of parametric oscillator in my slides.
Very good.
I'll tell the story in Caltech and in.
Okay. Oh, very good.
Very nice. Wonderful.
So we have 25 minutes.